Hello, Justin.
Oh, hi.
Hi. So
Hi.
co-host, welcome. Thank you very much.
Great. Thank you. I like this background. Where did you where did you get this from?
From you.
Yeah. I'm scared if you've seen the talk that comes from, you're gonna be sort of bored today because it'll be the same talk.
Well, I mean, people may ask different questions.
Right. True. Okay. So I will share my
Yeah, you
screen.
can share. Yeah, maybe we can start. Let me introduce you. Welcome, everyone. Welcome to Harvard CMSA Quantum Math and Physics Seminar Series. Today, we are very honored to have Justin Kaidi from Simon Center. He will be speaking about several of his recent work. The topic will be exploring non-supersymmetric string theory. And because there was a high energy physics journal club a week ago, many participants were discussing some of his works. So I hope those people in the audience can ask questions and feel free to interrupt because there are 90 minutes. So in any case, let's welcome Justin. Please take over. Thank you.
So thanks a lot for having me. So yeah, I've heard that the audience here is very diverse. There's condensed matter theorists, high energy people, maybe even math. So yeah, of course, if there's something that's outside of your specialty, please stop me at any time and ask, no matter how basic. So good. So I'm going to be talking about two sets of works that I had out in the last year or so. One is a pair of works that was done in collaboration with Julio Parra Martinez, who's now a postdoc at Caltech, and Yuichi Tachikawa. And the other one is slightly more recent. So actually, the topics of these two sets are not exactly identical. They're sort of different, actually, but what they have broadly in common is that they have something to say about non-supersymmetric string theory. And so that's going to be the theme of today's talk. And here, by non-supersymmetric string theory, I don't just mean the bosonic string, but rather I mean superstrings without space-time supersymmetry. Okay, so great. So I'm going to begin with a little bit of motivation here. So this is some ancient history. So back in the mid 90s or so, around the time of the second superstring revolution, it was discovered that all of the various superstring theories that we know and love are just different limits of a single underlying theory. And this gave rise to the iconic picture of the duality web that I have here. So we see, perturbative type 2a, type 2b, etc., are all just different limits in the moduli space of one underlying theory. Okay, so this is, of course, a great scientific triumph, but it's also, in a sense, a great philosophical triumph. I think that the idea that there exists one underlying fundamental theory is appealing to a lot of us. Okay, but actually, as it currently stands, there's some defects in this sort of unificational philosophy. So, for example, it's long been known that in addition to the supersymmetric strings, there exist various non-supersymmetric strings that are by and large consistent, and yet which lie largely outside of the duality web. So some examples of this, well, the most famous non-SUSY strings are probably the type 0 theories. There's type 0A and type 0B, which are largely exactly the same as type 2A and type 2B, except that you do a different GSO projection, as we'll review, so that we get, in these cases, non-supersymmetric spacetime spectra. There also exist analogs of type 1, so some unoriented type 0 theories. And I think that the precise number of them was actually somewhat unclear in the literature, so this is something that we'll try to follow up on. And there are also some non-supersymmetric heterotic string theories in 10D as well. So here the number will be somewhat important, so I call your attention to it. There are 7 non-supersymmetric heterotic strings in 10D, in contrast to, of course, the 2 SUSY ones that we're familiar with. Okay, so the point is there exist these strings, and except for some connections, which do exist, these things are by and large outside of the duality. Okay, and to make matters worse, there also exist string theories which are intrinsically in lower dimensions. So not just these 10D strings, but for example, something which really received a lot of attention are 2D strings. And so there are 2D analogs of type 0A and type 0B, for example, studied in, say, these works. There are 2D unoriented theories, which were studied, for example, in some works by Orrin Bergman. So in this case, there are known to be 8 of them. And there are some 2D heterotic strings as well, okay, studied, for example, in some papers by Davis and Zyberg et al. Okay, and here, again, I just want to draw your attention to the number here. So there are 3 2D heterotic strings in comparison to the 7 non-SUSY heterotic strings in 10D and the 2 SUSY heterotic strings. Okay, so those numbers will be somewhat important. So we have all of this stuff which lies naively outside of the duality web, but the philosophy that we're going to take in today's talk is that string theory is maybe the unique theory of quantum gravity, and hence, as long as these various cusps here actually correspond to consistent theories, they should be brought into the framework of the usual duality. So today we're going to try to explore some of the connections here. Okay, so one thing that should be emphasized is that I said so these cusps here should only be brought into the duality web as long as they correspond to consistent theories. Okay, and it's sometimes colloquially said that these non-supersymmetric string theories are actually inconsistent. And the reason which is sometimes cited for this is that the non-supersymmetric string theories generically have closed string tachyons. And so for that reason, people tend to write them off. So there actually exist some exceptions here. So to the best of my knowledge, there are 3 cases of non-SUSY strings which don't have closed string tachyons. But indeed, by and large, it's true that they do have closed string tachyons. But they shouldn't just be discarded for that reason, because the presence of a tachyon, of course, doesn't mean that the theory is inconsistent. All it means is that we're expanding around the wrong vacuum. Okay, so usually we're treating our perturbative string theory as describing fluctuations around, say, 10D Minkowski space. And so the presence of a tachyon just means that that's the wrong thing to do. We should instead treat it as describing fluctuations around a different vacuum, a different background, which actually corresponds to some stable vacuum of the theory. So as long as there exists one stable vacuum, the theories should be considered consistent. And something interesting that we're going to find is that in many cases, the stable vacua will actually be lower dimensional. Okay, and they'll actually, in many cases, correspond to 2-dimensional string theories. So for example, there will exist dynamical transitions from this tachyonic, say, type 0A theory in 10D to 2D type 0A. Okay, so such dynamical transitions are actually not new. They've been known to exist in the literature, but what we're going to do is show, that basically all of these theories that are tachyonic admit such a transition.
Sorry, Justin?
Yes, go for it.
Good question. So if you take this point of view, why wouldn't you also include the bosonic string?
You could include the bosonic string. And the bosonic string would also admit a 2D vacuum. But this was already known, so there's nothing really new to do there. But I could have added that.
They understood. So it's claimed to be the sig-1 string. That's the answer.
Say it one more time, sorry. The
So
bosonic case.
The stable vacua is described by the sig-1 string?
Right, yes.
Okay. But is this like completely established, or does some people expect?
Well, I don't know if it's beyond reasonably doubt established, but there are many papers to that effect. So I think it's fairly well accepted.
But your argument to describe this kind of tachyon condensation that goes from this type 20A to this 2D string theory would use a similar technology?
Not quite. So the technology it's not quite going to be the same. It's going to be a little bit different.
Okay, well,
I'll say it more clearly when we get there.
Mm-hmm. Thanks.
Mm-hmm. Great. Okay, great. So good. So that was actually all for the motivation. So before I tell you the goal of the talks, are there any other questions? Okay, cool. So
sorry, one more question. Are the string theory in dimension between 2 and 10 going to play any role? I mean, there are stable string theory between 2 and 10, for example.
There are.
Theory.
And so we're going to find some new stable string theories in dimensions between 2 and 10, but we're not going to talk about the existing ones. For example, there's a plethora of 4D ones that exist. And I can tell you something, well, I can mention something which is potentially related and at the final slide.
Mm-hmm.
But yeah, I'm not going to have much to say about, for example, those 4D theories.
Okay.
Mm-hmm. Great. Okay, any other questions? Okay, cool. So great. So let me tell you the goal of the talk now.
Wait, can I ask a question? Sorry.
Yeah, go for it.
I don't really know anything about these non-critical string theories. So are they UV complete?
Yes. So yes. Mm-hmm.
So why weren't these included in the original
Right.
story about
That's a good
the
question.
superstring?
Yeah, so you want to have worldsheet anomaly cancellation always. And so usually the way you do it is you have just a sufficient number of bosons so that and fermions so that you're in the correct dimension so that you cancel the worldsheet anomaly, the conformal anomaly on the worldsheet. But one way, so if you're in lower dimensions, you have less, say, bosonic fields to contribute towards the value of 26 that you need, for example, to cancel that anomaly. But one way you can make up for that is you could put in a linear dilaton profile. And so, yeah, the point is that all of these non-critical string theories have some linear dilaton. So they don't describe spacetimes which are, flat Minkowski space like people usually wanted. They describe these linear dilaton backgrounds where, in one half of your spacetime, it's very strongly coupled and it's sort of hard to interpret. So yeah, these non-critical string theories are going to have that as sort of a vice. So they all have this sort of nonlinear dilaton thing, which maybe makes them unattractive phenomenologically, but yeah, one could consider these. And
I see. Thank you.
Yeah. Okay, great. Good. So, right, goal of the talk. So we're going to have two goals. One is going to be to classify non-supersymmetric 10D string theories. And the other will be to find stable vacua for all of those which are tachyonic. And here, let me give an important caveat, by the way. So when I'm discussing stability, I'm only talking about perturbative stability. So these are really metastable vacua, but yeah, I leave the question of non-perturbative stability to more ambitious future works. Okay, so that's the goal. So this is somewhat ambitious to do all at once. So instead, I'm going to split things up into two parts, each illustrated by means of one single example. So in part one, we're going to illustrate the classificational framework by discussing unoriented type 0 strings. Okay, so that is these theories here. And then in part two of the talk, we're going to discuss stable vacua in the context of non-SUSY heterotic strings. So that's these guys here. Okay, so that's the goal. So let's get started on part 1. This is classifying unoriented type 0 strings. Okay, so good. So let me begin with a brief review here. So throughout this talk, we're going to be working in the NSR formalism in light cone gauge, which means that the worldsheet content of our strings is some left and right moving bosons, left and right moving superpartners, and there's going to be 8 of each of them. Now, the spectrum of the physical string is obtained from that of this NSR string by doing something known as the GSO projection. This is a projection of the state space of this theory onto some subsector, which satisfies various nice properties like closure of OPEs, mutual locality, and modular invariance, etc. Now, one nice way to think about the GSO projection, sort of geometric or I guess topological way of thinking about it, is to think of it as a sum over spin structures. And then the different GSO projections that you can do correspond to different possible phases that you can assign or insert into the spin structure sum. So to illustrate this by means of the example of type 2A and B, so type 2A and type 2B differ by GSO projection. And we can go ahead and diagnose this by looking at the torus partition function here. So here I've schematically written the torus partition function for type 2 strings. So what are the salient features? So importantly, I have separate spin structure sums for left and right movers. And here this box obviously represents a torus, but just to be explicit, let's say that the torus has default NS-NS boundary conditions. So this is anti-periodic, anti-periodic. The insertion of a line, each of these lines is a fermion parity symmetry defect line, which has the effect of giving an extra minus sign when I move a fermion along the cycle perpendicular to it. So this describes the RNS torus, and likewise, this is NSR. Oops. This is RR. Okay, so anyways, the sum over lines here is just supposed to be a sum over spin structures. And here I've inserted some phases, alpha left and alpha right, into the spin structure sums. So the different choices of alpha left and alpha right correspond to the different possible GSO projections. Now, I can't just insert any alpha left and alpha right into here. They have to satisfy some consistency conditions. And in particular, they have to be compatible with cutting and gluing of the worldsheet. And so when the dust settles, what one finds is that the consistent choices for alpha are as follows. So up to some normalization, on the NS-NS, NSR, and RNS tori, the alphas have to be all equal to 1. But on the RR torus, I have a twofold choice of plus or minus 1. And it's basically this twofold choice here, which differentiates between type 2A and B. Okay. So this is an old story of the GSO projection. And now we're going to go ahead and try to reinterpret this in somewhat new age language, which is sort of condensed matter inspired language of SPT phases. Okay, so let me give the obligatory 1-slide summary of what an SPT phase is. So for our purposes, an SPT phase is just going to be a gap theory with unique ground state on any manifold without boundary. So if I have a manifold X which has no boundary, the SPT phase assigns to X a partition function, which is an element of U1. Okay, good. So the SPT phase actually doesn't depend on the manifold X itself, but rather it only depends on the Bordism class of X. Okay, and so, well, let me recall for you the notion of a Bordism. Two manifolds X1 and X2 are said to be bordant if there exists a manifold in one higher dimension. Let's say these are d-dimensional. There exists a d+1 dimensional manifold which interpolates between the two. That is to say, its boundary is the union of the two. And we could also talk about Bordisms between manifolds with some structure. So let's say I have structure S, which is the structure group of the tangent bundle, and G, which is some extra G principal bundle. Then I could talk about Bordisms between manifolds with the structure S and G, as long as there exists an interpolating manifold along which I have an appropriate extension of this structure. So Bordisms give rise to some equivalence relation between manifolds, and then I could consider equivalence classes with respect to this equivalence relation. And the set of all equivalence classes forms a group, which is known as the Bordism group, and it's denoted by this omega here. Okay. So the point is that SPT phases provide a map from the Bordism group to U1. And hence, if I wanted to classify d-dimensional SPT phases protected by some G symmetry, all I would have to do is the standard math exercise of computing the Pontryagin dual Bordism group. That is to say, the group of homomorphisms from the Bordism group to U1. Now, I should mention here that there's this perennial confusion of whether we should talk about Pontryagin dual or Anderson dual. But I'm just going to be discussing torsion classes throughout, so it's not going to matter for me. All right, great. So now we know how to classify SPT phases. You just compute this group. And I should say one more thing, which is that in the presence of the boundary, we can have some gapless edge modes, and so we don't necessarily have to have this above story hold. So we're going to see some of those gapless edge modes in a moment. Okay.
Oh, excuse me.
Yes.
So the classification you use only capture the torsion, as you say, the finite group parts. Whether the Z class can be abandoned in the later part of your discussion, is that just because maybe some context in string theory you don't need them? Or
that's right. Well, we're also going to. Sorry.
Right. Those Z class, I think in certain cases can still be interpreted as SPT.
The Z class.
Z class, the free part.
Right, I agree. But we're actually only going to be looking at omega 2 in this talk, so I don't even think that there is any free part ever. So that's why it's not going to be relevant for us.
But how about other dimensions? Whether in the context you discuss, whether Z class play any role, or will you always only need the torsion, the finite groups?
So, I mean, we're only looking at string worldsheets in this talk, so we're only looking at omega 2. All I want to know are what topological or SPT phases I can put on the string worldsheet, and there's not going to be any free part that I can put on the worldsheet anyway.
Okay.
Yeah.
Okay, thanks.
Mm-hmm. Great. Okay. Good. Okay. So, well, that was the review of SPTs. So now let me give you an example of the simplest, in some sense, SPT phase, at least simplest fermionic one. So this is an extremely concrete system known as the Kitaev chain, or Meyer-Wanner wire. And this is actually so concrete that it's been realized experimentally. So people have built this thing in the lab. So actually, let me just ask the audience. So is everybody familiar with the Kitaev chain? Does anybody want a 5-minute review of what this is, or should I just assume that you know it? So maybe if anybody would like a 5-minute review of the Kitaev chain, please say so right now.
Yeah, I would like one.
Okay. So then let me quickly review what the Kitaev chain is. Great. Let's see. Okay. So let me use this blank slide here. So let's put ourselves in the shoes of a condensed matter experimentalist or maybe theorist. So how would I actually build this Kitaev chain? What I would do is I'd go ahead and I'd build a one-dimensional spatial lattice as shown here. So I have lattice sites 1, 2, ... n. So it's not a periodic lattice. And at each site, I can either have or not have some electron. Okay, so some Dirac fermion. So at the site I, there are some creation and annihilation operators, F, and they satisfy the usual algebra. Okay, and to each site, there is an associated occupation number, Fi dagger Fi, which can take values 0 or 1. Okay, so either it's occupied or it's not occupied. So now the sort of key trick in understanding this Kitaev chain is one makes some formal change of basis of creation and annihilation operators. In other words, some Bogoliubov transformation. So I rewrite F as Ci plus I di, and Fi dagger as Ci minus I di. And so clearly, by definition, Ci dagger is equal to Ci, and Di dagger is equal to Di. So these are now like creation / annihilation operators for some Majorana Fermi. So what I've done is I've effectively split up each lattice site into 2 lattice sites, 1, 2, n. And now there's separate creation operators for Majoranas at each of these 2 lattice sites. So C1, D1, C2, D2, ... Cn, Dn. Okay. And oh yeah, and so let me just note that the occupation number, when written in terms of CIs and DIs, you can check, it looks like 1 plus I Ci di. And so the fact that this is 0 or 1 means that I Ci di is plus or minus 1. Okay, so right now I've just written down some lattice, and what I'm going to do is I'm now going to give you 2 Hamiltonians, one of which I claim describes the topologically trivial phase, and one of them which describes the topologically non-trivial phase. And it's the latter which will be the Kitaev chain. So let me begin by giving you the trivial Hamiltonian, topologically trivial. So, okay, we're going to begin with this Hamiltonian here. So I sum 1 to n Ci di. Okay, so this is describing a trivial phase in the sense that this has a unique gapped ground state. Okay, even on this manifold with a boundary. Okay, so how do we see that this has a unique gapped ground state? Well, first, it's unique because these CIDIs here all take values plus or minus 1. And so clearly, I minimize the energy by just taking them all to be minus 1. Okay, so the ground state energy would be minus n. And good. And so how do I know it's gapped? Well, I know it's gapped because if I flip to the next excited state, I have to flip a minus 1 to a plus 1. And so I have an energy difference of 2, even at infinite volume. Okay. So this system has a unique gapped ground state. And pictorially, what it looks like is I'm linking this lattice site with this with this, and so on and so forth. That's what this Hamiltonian does. Okay, now let me tell you what the topologically non-trivial phase is. So, okay, now the non-trivial phase. So let me copy and paste this. Okay. So now I'm going to write down a second Hamiltonian for you. All right, looks like this, DICI plus 1. And so now I'm linking up this site with this site with the next, and this site with the next. So this no longer has a unique ground state. And the reason is the following. So it turns out that these DICI plus 1s also take value plus or minus 1. So I again minimize the energy by taking them all to be minus 1. So the ground state energy is minus n minus 1. But the key point here is that because we're looking at a non-periodic lattice, and because I'm also only assuming short-range interactions, there's a term which doesn't appear in the Hamiltonian, which is namely IDNC1. And this thing can also take values plus or minus 1. So depending on which value I choose, I have a twofold degeneracy of my ground state. Okay, so this is the non-trivial phase, and it's said to be topologically non-trivial because I cannot obtain this Hamiltonian from a continuous deformation of this one, at least not a continuous deformation which will preserve the gap on a manifold without boundary. Okay, so it's this topologically non-trivial phase here, which is referred to as the Kitaev chain. And the sort of physical hallmark that you're in this state is that at the edge, at the boundaries, you have these sort of dangling Majorana edge modes, which will together give you this twofold degeneracy that we saw. Okay. So this is the lattice picture of the Kitaev chain. So we're obviously more interested in the continuum. So then I would lift the one-dimensional lattice to a sheet when I add time. And in fact, I can consider manifolds without boundary too. If I put sufficient fluxes through it, I can also detect the non-trivial phase. So anyways, I'm on some 2D manifold is the point. So when I look at the relevant Bordism group, D is equal to 2. S, which was the spin structure of the tangent bundle, is equal to spin. Sorry, I think I said something wrong. S is the structure group of the tangent bundle. So in the current case, it's spin because I want to put some fermions on this guy. And there's no other symmetry in play. So the relevant Bordism group to look at is omega-2 spin of a point. And this is just Z2. So the trivial element of Z2 corresponds to this trivial phase. The non-trivial element corresponds to this non-trivial phase. And the fact that the group is Z2 means that if I stack 2 copies of this, I can continuously deform it to this while preserving the gap on a closed manifold. So, okay. So that's the Kitaev chain. As you can see, all it took was very elementary quantum mechanics to understand it. But the beautiful thing is going to be that it's exactly that simple system which tells us the difference between type 2A and type 2B, as we'll now see.
Thanks for the review. It's pretty nice.
Mm-hmm. Okay, great. So excellent. So now we know what the Kitaev chain is. So all I have to tell you is one more thing, which is what is the partition function of the Kitaev chain on closed manifolds. Okay. I told you that for SPT phases, it should always be an element of U1, and indeed, the partition function of the Kitaev chain is known to be just -1 to something called the ARF invariant. Okay. So this is some simple math quantity, but I'm not going to tell you the definition of it because we won't need it. Instead, I'm just going to tell you what the relevant values of this partition function are on the manifolds of interest to us, which are just tori with various spin structures. So what we find is that on the NSNS, NSR, and RNS tori, this always evaluates to 1, whereas on the RR torus, it does evaluate to -1. And now I think that we already see how this is related to string theory. If we go back here, remember I told you that type 2A and type 2B differ just by a choice of this phase alpha, and that alpha was equal to 1 on the NSNS, NSR, and RNS tori, but could be plus or minus 1 on the RR torus. So the point is that the non-trivial phase with the -1 here looks exactly like the partition function of the Kitaev chain, and hence we can now sort of shift our interpretation of this GSO projection. Instead of thinking of type 2A and type 2B as having the same exact worldsheet theory, but different sums over spin structures, we can think of them as having the same sum over spin structures, but the actual worldsheet theory differs, and it differs by this subtle topological term, this ARF invariant. So that is the point of view that we're going to take.
Oh, may I make sure whether the alpha L and alpha R, the L and R left and right can choose independently?
Good. So yes, indeed. So I sort of lied. So right, what you really should have looked at in this case, because I have 2 different spin structures, is omega-2 spin of BZ2, where the extra Z2 allows you to have separate left and right moving spin structures. And it turns out that this is not Z2, but rather Z2 squared. So we would naively expect there to be 4 type 2 theories, right? Well, obviously, so the generators of these are ARF of the left moving spin structure and ARF of the right moving spin structure.
So there are 2 types of fermion parity, and there could be additional symmetry X on those 2 types of fermions.
Right, the left and right moving ones. Mm-hmm.
Which we might discuss later.
Yeah,
like
right.
Like the D-pin.
Yeah, so I actually was not planning on talking about D-pin, but we can talk about D-pin afterwards, yeah. Actually, there's something I wanted to ask you about D-pin, but we can do that towards the end. Okay, great. So yeah, so as Juven just said, really there's an order 4 group which classifies GSO projections for type 2 theories, but it turns out that 2 of them are not physically distinct. They're related to the other 2 by space-time parity flip. So that's why there's only two theories, type 2a and type 2b. Okay, so what I said about the Kitaev chain with just omega 2 spin of a point is actually literally true, not in that type 2 case, but in the type 0 case. Because in the type 0 case, unlike the type 2 case, I have only a single spin structure. I identify the left and right moving spin structures. So in the type 0 case, what I said is literally true. And so I have type 0a and type 0b, sorry, and type 0a, and they differ by exactly the generator of this dual Bordism group. That is to say, this ARF invariant here. Okay, and so what I was advocating a minute ago was that instead of interpreting this as the same worldsheet theories with different spin structure sums, I interpret it as the same spin structure sums, but now I just look at the worldsheet theories as being differing by this ARF. All right, so good. So let's just go ahead and now apply this to the one example I had promised you before we sort of switch to part 2 of the talk. So I promised to try to classify unoriented type 0 strings. So now we see how to do this in a fairly easy fashion. So the two possible worldsheet structures, the structures I can have on the type 0 worldsheet are pin minus and pin plus. So if I want to classify all of the GSO projections, I should just compute the relevant dual Bordism groups for pin minus and pin plus. And these are known in the math literature already, so it's Z8 and Z2. So I would conclude that I have, for example, 8 different pin minus type 0 theories, and the worldsheets of those theories differ by addition of the generator of this dual Bordism group, so this ABK here. Okay. Right, so that's how this classificational framework works. Okay, good. And oh yeah, so this SPT point of view is not just useful for classifying the GSO projections, and hence the string theories themselves, but it's also very useful for understanding the objects in these string theories. For example, using this SPT language or point of view, we can actually get a very nice worldsheet rederivation of the well-known fact that stable D-branes are classified by K-theory. Okay, so for example, we can rederive the fact that type 2a and type 2b strings have D-branes which are classified by complex K and K1 theory, respectively, by just analyzing those dangling Majorana modes that we had at the end of the non-trivial phase. Okay, and likewise, there exists some nice generalization of this K-theory classification for, say, these 8 pin minus strings that I have here, okay, which gives rise to some rich spectrum of stable D-branes. All right, great. So that was the classificational framework. And well, one thing that we find is that if we look at all of these pin minus theories that we just found, it turns out that they're all tachyonic. And this now motivates us to turn to the second part of the talk, where we see if those tachyons can somehow be remedied by condensing to some lower dimensional vacuum.
Can I ask a question here?
Yeah, go for it.
So there's some recent work from Cameron Vafa and Jake McNamara about this potential non-perturbative boundary for type 2b, and it's supposed to be stable. But that's not in this list?
So are you talking about these, which one are you talking about concretely?
Just trying to understand the kind of D-brane that's classified by your analysis. Do you assume the D-brane has to be described as a boundary condition for some weakly coupled worldsheet string theory?
Yes, right.
So those kind of non-perturbative objects would not be accessible?
I imagine so. I mean, for example, yes, this doesn't capture a lot of non-perturbative objects. For example, it doesn't capture the NS5 brane, etc.
Yes.
For which you would have to appeal to twisted K theory. So indeed, all we're doing here is so the analysis here is we basically look at the Clifford bundles at the endpoints of the open string,
Yeah.
And then we just use the definition of K-theory in terms of Clifford bundles.
Right. So that only access this derivative. Okay.
Yeah. Right. Great. Okay. Any other questions on part one? Okay. Great. So next I want to tell you about stable vacua, or metastable vacua. Really. Okay, and here we're going to be focusing on the tachyonic heterotic strings. So first, let me remind you about the tachyonic heterotic strings. So the tachyonic heterotic strings that we're going to discuss were originally found by KLT and roughly contemporaneously by Dixon and Harvey. So we're actually not going to follow their way of constructing them because I think in hindsight, there's a somewhat easier way of doing so. So, okay, the way we're going to proceed is as follows. We're going to start with the usual worldsheet content of the heterotic string. So we have some left and right moving bosons. We have some left moving superpartners for those bosons. There's 8 of each. And on the right-hand side, I have a bosonic string. So in addition to these 8 right movers, I need to have 16 more right moving bosons. And I'm going to go ahead and fermionize those to 32 right moving fermions. So this is going to be my worldsheet content. Now, the simplest possible partition function I can imagine writing with this worldsheet content is just this one here. So I have this Dedekind function from the bosons, and then you can see that I've identified all of the left and right moving spin structures. So there's just one spin structure I'm summing over, and so I have the 8 left movers and 32 right. Now, these boxes represent fermion torus partition functions, which admit known expressions in terms of theta functions. So I just plug in the theta functions, and then I can obtain the Q expansion. And the first terms in the level matched part of the Q expansion are shown here. So I have 32 QQ bar to the -1 plus 4032 plus ... And so this partition function would describe a tentative theory which has 32 tachyons and 4032 massless fields, which it turns out can be interpreted as bosons. So they can be interpreted as a graviton, V field, and a dilaton, all in 10 dimensions, and 496 gauge bosons of SO32. So this partition function describes a tentative non-supersymmetric SO32 heterotic string. And now if we take this as our seed theory, we can obtain additional tachyonic heterotic strings by doing the following. So we note that the worldsheet theory I just mentioned has a Z2 to the 5th global symmetry. Okay, so that symmetry is generated by 5 different Z2 elements, each of which looks like Pauli sigma 3, tensored with a bunch of 1s. Okay. In particular, I tensor it with 1s so that in total it's a 32 by 32 dimensional matrix, and it acts on the right moving fermions in the vector representation. Okay. So because each of these elements is just Pauli sigma 3 times a bunch of 1s, clearly each element acts as -1 on half of the fermions, right moving fermions, and +1 on the other half. All right. Good. And now we can go ahead and we can gauge some subset of this Z2 to the 5th symmetry. Okay, let's say Z2 to the n for n between 0 and 5. Okay, and if we do so, then we get a series of 6 different theories labeled by n from 0 to 5, with then some spectrum of tachyons, massless fermions, gauge bosons, and gauge groups as shown here. Okay, so one thing I should say is I'm not going to be careful at all about the global structure of this gauge group. So just interpret this as gauge algebras, really. Okay, good. So, right, and I wanted to say.
Naive question, maybe it's really naive. So when you write down this partition function with 4032, and this 4032 somehow you associate with the massless bosons, and somehow they are separate into several different types with different the space-time Lorentz spins. I just wonder how was that being read? For example, graviton spin 2, I suppose didoton spin 0, gauge boson spin 1. How is that data being read? This is really naive from non-string theorist.
Oh, sorry. I see. You're just asking how do I know I can decompose it?
Yeah.
Yeah. So it's sort of like a confirmation bias. You get this number, and then you see that it can be decomposed in this way, and then you recognize that such a theory already exists in the literature. So it's really that point of view that I'm taking here.
Well, you can just build them explicitly from outside.
So yeah, exactly. So if you really wanted to, you could just go ahead and use the worldsheet content I wrote down here to build the relevant vertex operators. So that's what's done in, for example, Polchinski, etc. But for our purposes here, we could just check that this is the theory that already exists.
Okay.
Mm-hmm. Right. Okay, great. Okay, any other questions on that? Okay, good. So, so we went ahead and we gauged the C2 to the N. So when I do so, I break the SO32 symmetry that I had before down to some subgroup, SO2 to the 5 minus N times, well, the remainder. Okay, and this SO2 to the 5 minus N is going to be sort of important for us. So we can see that this SO2 to the 5 minus N survives in the gauge group. This guy gets enhanced generically, but this guy doesn't. So for example, I have SO32 here, SO16, SO8. I have O4, which comes from the SU2 squared here, and then O2 is the U1 part of this U16. So I have this residual SO2 to the 5 minus N piece. And the important thing is that the tachyon always transforms in the vector representation. Okay, good. So we now have these 6 tachyonic theories, and we're going to try and condense the tachyon now and see if we can identify stable vacua. So to do so, we're going to follow the example of Hellerman and Swanson, who basically did the same exercise for the specific case of E8, this E8 theory here. So we're going to extend this to these other theories just by porting their results. Okay, so when we condense the tachyon, we're going to produce a worldsheet superpotential, which looks as shown here. So I have the tachyon profile here, which recall has a vector index A. This is a vector index under SO2 to the 5 minus N. And I have to write down a 1, 0 superpotential on the worldsheet, which contains that tachyon profile. So basically the only thing I can do is I can contract the vector index with the vector index on the right moving fermions, lambda. In particular, it's those lambda which were left invariant under this Z2 to the N, right? They also transform in the vector of this SO2 to the 5 minus N. All right, so I have this worldsheet superpotential here. And now I want to go ahead and plug in a specific tachyon profile here. So I look at the linearized equations of motion for the tachyon profile, and they look as shown here. So phi here is the dilaton. And now I just want to look for solutions to this equation. And it turns out that one solution is as shown here. You can just plug it in and check. So what does this solution look like? I have a linear dilaton. So phi is linear in the x minus coordinate, one of the light cone coordinates. And the tachyon is exponential in the other light cone coordinate, x plus. And it's also linear in spatial coordinates. So each component of the tachyon, of which there were 2 to the 5 minus N, is linear in a different spatial coordinate. Okay.
I have 2 questions.
Yeah.
First, when you call it superpotential, this is not what's normally called superpotential because you're in 1-0 supersymmetry rather than 2-0. This is a question about terminology.
Okay, yeah.
This is not like the object which enjoys non-renormalization theorems and so forth.
Right.
So this is just for clarification. The second thing which is not clear to me is that the signature of your space-time is Lorentzian here, right?
That's right, yes.
And the Lagrangian has explicit x minus and x plus dependence.
That's correct.
So the theory on the worldsheet is not a standard field theory.
Right. Well, it's not going to be, let's see.
So you're going to get exponential in time.
That's right. I'm not going to get a local, I guess, field theory, right? I'm going to get something which looks like e to the x plus times some other stuff.
Well, the x plus has an x10 or x9 or whatever special coordinate. That doesn't bother me. But the x0 that sits in the exponent does bother me in the action. So you have an interaction that has negative sign kinetic term and interactions that grow exponentially.
Right.
So is this something that would bother us? Is this a meaningful field theory, or how should we think of it?
Right. So So the way that I would like to interpret this is I would focus on the region, which, so, okay, first let me say that if I plug this into this super potential and then I integrate over the superspace coordinate, the actual scalar potential that we're discussing right now is this guy here. And so the sort of worrisome term is, right, the e to the x0 that you have here. So the only time that I really want to think about this worldsheet field theory is at x plus goes to infinity. And so in that regime, I suspect that things are well defined because I integrate out these XA fields here. And then I sort of get rid of these terms. So at these late light cone times, I think what I get is a standard worldsheet field theory in effectively lower dimensions. I don't know if that makes sense.
You can consider another field theory which would lead to perhaps a consistent string theory. I'm just questioning whether the worldsheet Lagrangian with the potential that you wrote here really makes sense, given that x0 has the wrong sign.
Right. Yeah, I understand that issue. So I guess the way that I would like to say it is as follows. So here, the way we were trying to interpret this is as some dynamical transition where I have this potential and then there's, in a sense, a worldsheet RG flow whereby when I go to these late light cone times, I get something without these worrisome terms. But instead of that, I could just look at the lower dimensional theory on its own. And that lower dimensional theory, there's nothing sick about it. So it's a completely normal worldsheet theory in lower dimensions where I have less scalar fields and then a space-like dilaton to cancel the conformal anomaly.
I see. Thank you.
Great. Okay, any other questions? Okay. Thank you for all the questions. So let's see. Did I want to? All right. So something I was going to say, right, was that these are solutions to the linearized equations of motion, but they are also alpha prime exact solutions to the stringy equations of motion, it turns out. So maybe afterwards I can go ahead and sketch for you the reason why. But So, okay, so anyways, the upshot was that I took this solution, plug it in here, get the scalar potential that I have here, and then as we just reviewed, the sort of point of view is that as x plus goes to infinity, because I have this mass type term for the spatial coordinates, which is proportional to this exponential here, I would assume that the fluctuations along these directions are suppressed, and we get a theory in effectively lower dimensions. And that theory in effectively lower dimensions doesn't have any of this stuff. It's just a normal looking worldsheet theory, but with a space-like linear dilaton profile. Okay, and so those intrinsically lower dimensional theories for n is equal to 3, 4, and 5 end up being in dimensions 6, 8, and 9. Okay. And just at the level of the partition function, you can do this integrating out, and then you can read off the spectrum of massless fermions and gauge bosons, as well as the gauge groups. Okay, so what we've identified is these potentially intrinsically lower dimensional string theories. And then you could play the usual games that one likes to play, like you could look at the low energy effective action. Usually this is some supergravity theory, but because these strings are not supersymmetric, it's just some gravity plus gauge theory in this case. But you can check that, for example, you have cancellation of all of the local and global anomalies. And so there's some cute versions, lower dimensional versions of the Green-Schwarz mechanism that come into play here. So everything seems to work out nicely for these guys. Okay, so good. So we've identified these potentially perturbatively stable vacua for the n is equal to 3, 4, and 5 cases. And now I'd like to turn to the n is equal to 0, 1, or 2 cases. So I can't just naively do the same thing that I did in these cases. The reason being because, at least for n is less than 2, if I were to just plug those into the formula for the dimension, I get a negative dimension, so that's not good. So instead, in this case, what one does is one just condenses down to d is equal to 2. So we use the same profile that we had here, but now we only condense 8 components of the tachyon. So one might worry that there are still some components of the tachyon which remain uncondensed and might indicate some instability. But because of the following fact, that's not anything to worry about. So it turns out that in d is equal to 2, the dilaton background gives one an effective mass, which is enough to shift the tachyon mass to be 0. So the tachyon actually becomes massless. And so what we conclude is that for these 3 theories, with n is equal to 0, 1, or 2, we get 3 different 2D theories, and they have this spectrum of massless bosons and fermions and these gauge groups here. And in fact, these 3 2D heterotic strings are exactly those which had already been known in the literature. So what we've done is we've provided some connections in that big plot I had shown before, that big web, whereby we've obtained some dynamical transitions from the 10D tachyonic heterotic strings down to all 3 known 2D heterotic strings. Okay, good. Okay. So that's basically all I wanted to tell you in part 2. So now I want to begin with the conclusions. Are there any questions before I move on to the conclusions? Okay, so let me conclude then. So in this talk, there were 2 parts. So in the first part of the talk, we discussed how the worldsheets of different string theories can differ by subtle topological terms, and how these terms could explain different GSO projections, D-brane spectra, and orientifoldings allowed in the theories. And then in part 2 of the talk, we discussed how for those non-SUSY string theories which are tachyonic, they often admit lower dimensional stable vacua, and in many cases, these are actually known 2-dimensional strings. So what are some possible future extensions? So on this slide, I'll just give some sort of sketchy ones, and on the following slide, I'll give a more concrete possible future extension. So what are some things that would be interesting to think about? Well, one is we could consider putting these SPT phases on heterotic string worldsheets. So to see that this is probably going to lead to something interesting, all we have to do is look at the order of the relevant Bordism group. And it's something upwards of 65,000. So either there's going to be a whole lot of new GSO projections, or there's going to be some massive amount of redundancy, whereby a lot of the theories obtained by these GSO projections are identified. And either way, I think it would be interesting to understand. Something else that we could consider are worldsheet domain walls. So these would be like domain walls between the trivial and non-trivial SPT phase on the worldsheet. So they would be like domain walls between type 2a and type 2b, say. And more down to earth, one could revisit old orbifold literature. So there's this whole story of discrete torsion, and one could go beyond that paradigm by, instead of using group cohomology phases, we could use these cobordism elements. Okay, and so then maybe something which is slightly more concrete that I think would be interesting to understand better would be the following. So string worldsheets come equipped not just with some structure group of the tangent bundle and some G-principal bundle, like we've been allowing thus far, but they also come equipped with a certain map, that is to say the map to the target space X. And hence we could consider adding elements to the worldsheet which are not just omega-2 spin of, say, a point, like we've been doing thus far, but omega-2 spin of X. So this is obviously a bigger group than the group that we've been studying thus far. And hence there are going to be more elements in it that can be used to add to the worldsheet, and hence, in some sense, differentiate between different string theories. So let me say a little bit more about that. So this group here can be computed by some math procedure known as the Atiyah-Hertzsprung spectral sequence. And well, one of the morals of the Atiyah-Hertzsprung spectral sequence is that as a set, not quite as a group, but as a set, this group omega-2 spin of X is equal to the omega-2 spin of a point that we've been studying thus far, plus H1, so this cohomology group of X with Z2 coefficients, and then H2 of X with U1 coefficients. And so now we could ask, what do these additional pieces here tell us? So the first piece, just to remind you, it was generated by the ARF invariant, and it told us the difference basically between A versus B type theories. Okay, now what about the generator of this? So the generator of this is some flat B field. And so, well, clearly what this tells you is it tells you about worldsheet theories with different values of the NSNS2 form, okay, differing by some flat piece. So that's what this guy does. It's not hard to understand. Slightly more subtle or surprising is the presence of this piece here. The generator is some Z2 gauge field A. And I think that this field A is, well, the way to interpret it is that it's what gives rise to the separate left and right moving spin structures in the type 2 case. Okay, so in a sense, this piece here tells you about type 0 versus type 2. Okay, so in some sense, this extra data, the 0 versus 2 is sort of part of the B field in a sense. Okay. And so, well, we saw before that using these SPT phases and understanding these Clifford bundles that come from the edge modes allowed us to rederive from a worldsheet perspective the K-theory classification of D-branes. So you would now like to do the same thing in the presence of, say, this B field and also this Z2 gauge field A. And it turns out that there's precisely such a nice object to use, which is twisted K-theory. Okay, so of course, it's been known since the original works of Witten that twisted K-theory is relevant when you're looking at branes in the presence of a flat B field. But something that at least I hadn't appreciated is that there exists a twisted K-theory which also accounts for this Z2 gauge field A. Okay, so in other words, the K groups are labeled by some alpha, which is not just in Z2, but also it takes values here too. Okay. And so something which I still don't understand, but I would like to think about more is the following. So I told you that this equality is true at the level of sets, but not as groups. So there's some interesting mixing between the group laws of the Z2 gauge field and the NSNS2 form piece. And so in particular, if I take an element A comma B of H1, H2, then the group law is that they add in this way. Okay, so the group law for the A's is normal, but in the B's, I pick up this extra shift here. And it would be interesting to understand the physical implications of this. Okay, so that's all. So thank you guys for listening.
Thank you very much, Justin, for the wonderful seminar. Thank you.
Thank you.
A question from the audience.
Can I ask a question? So Justin, would it be interesting to look at, instead of the Bordism in your last slide, the Bordism group from the worldsheet with string structure to the target, but with actually the string structure? I remember that also has the ability to see this B field background. I was wondering what's the relation, and also to the topological modular forms.
Right. Well, so I mean, string structure is something that you have in the bulk, right, in the target space, not on the worldsheet.
That is true. That is true.
Right. So here, these are phases that I'm trying to add to the worldsheet, which doesn't have string structure.
Okay. So the TMF, in any case, is on top of what you have said.
That's right. So, right.
Which is related to the target space.
So TMF. Let's see, how should I say this? So if I were looking at, let me say it this way: omega spin is to KO or K as omega string would be to TMF.
Right.
Right. So in other words, there's some analog of the ABS orientation for TMF in the string structure.
Yes.
Yeah. So yeah, I mean, from the worldsheet perspective, I'm not sure if that plays any role.
Well, but from the worldsheet perspective, you have 1,0 supersymmetry. You can talk about TMF.
Yeah. Right. Thinking of TMF as the moduli space of such as SCFTs.
Right.
Yeah. Indeed, I agree.
It's to give a finer structure if you want to classify the worldsheet, string worldsheet theories. Finer than just the SPTs.
Right. Yeah. Right. I mean, SPTs at the end of the day, all I'm doing is I'm taking the usual, nice geometric type worldsheet theory, which has the x's, et cetera, and then adding some topological terms on top of it. But I think the upshot of TMF is that I can even classify, the non-geometric worldsheet CFTs, and it's much broader, I think, than what I'm talking about here.
Yeah.
Can I ask a question?
Yeah, please.
Hi, Justin.
Hi.
Nice talk.
Thank you.
So the difficulty with closed string tachyons has always been that we don't have a handle on the tachyon potential. In particular, closed string field theory doesn't help.
Right.
So why is it that you didn't need to know the tachyon potential? Or in other words, why could you linearize the tachyon equation?
Well, let me think about it. So my understanding of the origin of this equation is, well, simply that this is what's required for T to be a 1/2 superconformal primary. Right. Yeah, I mean, beyond this term, I don't think anything else is allowed by the symmetries on the worldsheet, is there? I mean,
I think from the worldsheet point of view, all the terms, I mean, if you think about it from an alpha prime expansion in the limit that you want to take, in which x plus goes to infinity, those will be further suppressed by, I think, by the alpha prime expansion. So anything that has, is higher order than alpha prime will be suppressed in the limit of x plus going to infinity. I think that's sort of what you want to say. So for instance, dot, dot, dot you have there. You're able to drop in this limit.
Right.
Is that right?
I need to think about it a little bit more, sorry. Yeah, it's a good question, and I don't want to say.
I mean, the analogous question for open string theory was it took a long time for people to find the open string tachyonic vacuum, and it required understanding of the tachyon potential. That it required solving open string field theory and finding effectively what the tachyon potential was in the open string, but somehow here, you don't need to know any of that. You're saying it's a simple equation.
Yeah, I think so. Yeah, let me think slightly more about it. So I don't want to say anything wrong, especially when being recorded. So let me get back to you on that.
So, here's an easier question. I mean, these on this page, the 6, 8, and 9 dimensional heterotic strings,
right?
Are they stable? Are they really tachyon free?
They are tachyon free. Yes, they are tachyon free.
Were these theories known before?
No, to the best of my knowledge, not. So of course they have linear dilitons.
Yeah, sure.
But I think to the best of my knowledge, no. But yeah, these would be new intrinsically lower dimensional theories. Oh, sorry.
So previously we only thought that only 2-dimensional strings can be tachyon free, can be stable.
Well, so there are some. That's true. So actually, sorry. Let me say this E8 case was known by Hellerman, but these two are new. So right, there's basically two mechanisms for stabilizing a theory. So one is to go to 2D. And then in 2D, you still have some components of the tachyon. So there's still some relevant operators, but there are no normalizable excitations that have, this runoff behavior. They're all, sort of stable. So here we're using a different mechanism whereby we're actually just getting rid of all of the relevant operators that are allowed by the symmetries. We're doing this by this sort of worldsheet RG flow where we integrate out enough fields that I just can't construct anything that's relevant. So that's actually sort of the strategy here. So, so these would be actually new, and I think it's interesting to see if there are more cases like this. But right, so by and large, they're all via that first mechanism where you go down to 2 dimensions. So out of all of these cusps here, the unoriented type 0, the type 0b, type 0a, all of these guys go to 2-dimensional theories, as well as 3 of the heterotic ones. So it's only those 3 heterotics that we just talked about that have higher dimensional stable vacuum.
I see. Thanks.
Thank you.
Perhaps we can end the recording first, and then we can discuss more freely.
Okay, sure.
Let's